All right, another exciting day in Trig. So actually, piece of business to discuss before we get rolling. So we can definitely, we're probably gonna get through this lecture, no problem. Do we want to have the quiz next time, or do we guys want to push it till next Tuesday? Tuesday? Oh, looks like you're outvoted, Brenna. All right, now beware, if we do that, we are lecturing the next section next class, right? It's not just free day or anything, okay? All right, and that's fine. I was like, since we're supposed to basically be like a light day today, but since we basically got to get through all this.
Is it just the quiz game pushback or the home fun and the?
Yes, I'll push it all back. I'll fix all the dates today or tomorrow. Yeah, no, that correspondingly pushes everything. When I say quiz, everything follows that.
Everything, okay.
All right, okay, so, and that actually allows us to do a little tangent too. And when I say tangent here, I mean tangent, the conceptual idea of going on a tangent, side note, all right? Not the trigonometric function. And mostly I want to back up and I want to mention a couple things about factoring. So everything in trig comes back around to algebra, right? We have those 5 techniques, common denominator and factoring and conjugate, right? Those are algebra concepts, but factoring needs a little bit more explanation. So first of all, GCF, right? This is the biggest one we do all the time, greatest common factor, right? X squared plus 7x. GCF is always the first thing we do. Pull out the common term. Right? We should all be pretty familiar with that. We talked about this one last time, grouping. When you have terms that are similar, let's see, make sure this works. All right. We look at the terms 2 terms at a time, right? So when you have 4 terms, you look at the terms 2 terms at a time, and the first ones I say, okay, what can I pull out of the first 2 terms? I can pull out an x. What can I pull out from the second 2 terms in this case? 1, right? And that's important to note. So when I pull those all the way out, x plus 1 comes out, and I know grouping worked because what is in the parentheses match. And I can even write that as x plus 1 quantity squared. So factoring is a big one. Those are by far the 2 most common techniques. The other big one, right, is what's known as the diamond. The diamond needs a little bit of explanation to start. So the other big thing we do is we factor quadratics. Quadratics are massively common in all of mathematics. Factoring a quadratic, all right, and quadratic really includes just these 3 terms, right? X squared, x, and then x to the 0. The AC diamond method allows us to break this down, all right, by identifying a couple of terms and then being able to pull this apart. Now, a lot of people, when they see quadratics, all right, so looking at a simple example here. The idea is that this factors into 2 binomials, all right? Some x plus some x plus, all right? There's a term here, a term here, a term here, and a term here. We should And ideally, if you could look at this and identify what term goes in each of these pieces, that's fantastic, all right? Being able to look at that and see how that pulls apart is a little bit difficult, so the diamond helps us do that. Because the possibilities that go, all right, in that first term, 1 times 6, 2 times 3, 12, that's 1 times 12, 2 times 6, 3 times 4. These values can be any combination of these 6 numbers in these last 2 spots, right? These 4 numbers can be any combination in those. So basically what we have is 4 times 6 times order matters 2. 4 times 6, 24, 48. There are 48 combinations here, okay? That's a lot of combinations of how this can work. So if you were able to look at that and see that, fantastic. I'm a terrible guesser. It takes me forever to get through all those values. So here's what the diamond does for us. Okay, so back to this guy. Basically, write the diamond out. This top term I have listed as A times C. Right? This is in order, ax squared plus bx plus c. So A times C, that means this is 6 times 12. 72. The B term, that middle term, that goes down here, 17. So now what I do is I say, okay, what multiplies to 72? What 2 numbers multiply to 72 and sum to 17? Now, since all these numbers are positive, this is the simple case. I didn't even have to worry about the signs here. I know that the factors are going to be positive as well. But it could be one is a positive, one's a negative, both are negatives, right? Depends on what the signs are of the AC term and the B term. But basically, I just say, okay, what 2 numbers multiply to 72 and sum to 17? Can anyone think of them?
8 and 9.
8 and 9, that's exactly correct. And we see how that works? Multiply up here, sum down here, right? If this was like -1 and this was -72, all right, how would these values change? This was a -1 and -72.
8 and 9.
Be -9, +8. Similarly, this was -72 and +1, then it'd be vice versa. All right, so it will always work. Those 2 values added together, right, make the bottom piece of the diamond, and sum make the top. All right, so then what you do is rewrite the B term using the factors. So this becomes 6x squared and 12. I don't touch that. The B term was 17x. Now I'm going to break it up into the factors. That 17x becomes 8x and 9x. Now if I combine those together, 8x plus 9x goes back to 17x. So this got a little bit worse before it's about to get a bunch better. Now I have 4 terms. What should I do?
Factor by grouping.
Factor by grouping. Of the first 2 terms, what can I pull out?
2x.
Of the second 2 terms?
3.
Did factor by grouping work? Which means, did the diamond work?
Yes.
And that's basically how you tell. So what did 2 factors become?
2x plus 3 and 3x plus 4.
And looking back, right? 2 and 3 were a possibility. 3 and 4 were a possibility. I was like, where the 3 goes and where the 2 goes does matter, right? Because it can't be 2x plus 4 and 3x plus. So where these sit, that's the hard part of just looking at it and guessing. But this algebra concept, again, is very, very helpful. Okay, so what we have there Okay, so we basically talked about, this is when we have 4 terms. This is when we have 3 terms. All right, there's one other big case. Well, 2 in. When we have 2 terms, and there's really 2 big cases of 2 terms. One we've already talked about. A difference of squares, basically how we create the conjugate. A squared minus b squared. A minus b, a plus b. Now, as a note, this is a quadratic, and you can do this with the diamond, actually. Because if I have x squared minus 9, that becomes what times what? Go ahead, Jada.
X minus 3 and x plus 3.
Now I can do that with the diamond. All right, the top of the diamond would be -9, and the bottom of the diamond would be 0, right? Because there is no middle term. And then you can actually figure that out, and you'll be like, oh, let's see what multiplies to -9 and sums to 0, -3, +3. This is just better if you could just look at these ones. You should be able to look at and identify. So difference of squares is one variation, and the other that you're probably less familiar with. Sum or difference of cubes. Now you can just write the formula down. But actually, I just want to identify the method, which you can always remember this. First of all, we use soap. Always use soap. Because this is the thing. We have so much new information all the time. If you have if your cheat sheet is full of algebra stuff, okay, your trig stuff starts getting pushed off. When you go to calculus, if it's full of algebra stuff and trig stuff, your calculus stuff can't fit on there. So ideally, depending upon how far you are going in mathematics, you need to start committing some of this to memory. All right? Because the further we go in any, and this is true for any field, right? I mean, this doesn't but everyone in here is, and I think we already talked, everyone's going to calculus from here, right? And this is algebra stuff that needs to start getting committed at least for one more semester. Okay, so same, opposite, always positive. This identifies the sign, okay? So, let's do a specific case. If I have a cubed plus b cubed, same, opposite, always positive. That identifies my signs. And similarly, I guess let's write it out individually for both, just so we can verify. Same, opposite, always positive. So what this leaves is I have 1, 2, 3, 4, 5 terms to fill in. All right, so now we're going to do the bunny. So I have an A and a B because the whole point of cubes is you've identified something cubed plus or minus something cubed. So we've identified our first 2 terms. Because you identified what is being cubed. Then we do the bunny in order to find the next term. A times A times B, B times B. And that identifies our that's how we identify our terms. Now again, like I said, you can just have this formula written down, but all right, if you use soap on the bunny, that is what we call wash the bunny face. All right. I don't think I had any of you in algebra, but this is a big part of the polynomial dance. All right, factoring in general is a big part of the polynomial dance. All right, so everyone stand up for a minute. And let's just practice a little bit. Jada, you don't have to do this excessively. All right, so, all right, how do polynomials go? When I say polynomials, what graphs are we referring to? What is a polynomial? No one knows. Stuff with x's to a power. That's what a polynomial is. All right, doesn't matter what power that is. So what's the very first one? X to what power?
X squared.
X squared. What's that graph look like? A parabola. Everyone up? You can do it while sitting. Okay. I just didn't want you to stand in case your leg hurts. All right. Well, how about negative parabola? How about cubic? How about negative cubic? All right. And then that's the main step of the polynomial. Okay. So our pieces here that involve factoring. Whoa, we're not done. That was just the intro. All right. So we do the diamond. All right. So now we start getting into the good stuff. All right. We do the diamond. We do the diamond. All right. I'm working with the hip hop here. Do the diamond. Do the diamond. All right. Well, we're all in this together. Come on. I was like, it's going to be on the test.
It is not.
All right. Do the diamond. All right. Then the other couple of things we do. So wash the bunny face. Wash the bunny face. Wash the bunny face. All right. You guys, and the point is this is all algebra stuff that I want you to remember. How do you remember stuff in general?
I do.
By making an association in your mind. Are we all going to remember all this? If next time I ask, we don't know, guess what we're going to do again? Not rhetorical. Guess what we're going to do?
The dance.
We're going to dance. And we're going to dance it again and again and again. All right? This is algebra stuff. All right? And again, the further we get in trig, the more this needs to just be ingrained. Okay, so that's the side note. And I mostly just want to talk about that because we were running out of time last time. And I saw everyone when I was doing factoring by grouping, everyone was like, didn't know what we were looking at. So along those lines, we want to establish the identity. Well, now back to what we were doing. So I want to establish this identity with all identities, all right? Where do we start? What do I need to do very first?
Sine and cosine.
Not methods. I have established the identity and I have that equals this.
Might be easier.
Pick a side, all right? And which side do I pick? The harder side, okay. So clearly looks like that side is the harder side. Okay. All right, now techniques. Okay, convert to sines, cosines. Done. Common denominator. Done. What's the next one? Factor. Does this look factorable?
No.
No.
Yes.
If it looks a little complicated, what should we do? Change it to x's. Does this look factorable? And it is easier to recognize in X's. That's why we do this. Okay? When I change it to X's or Y's, whatever. Okay, technically this was sine, so we should have done Y, but we only have one here. All right. Then, all right, now I'm looking at a quadratic. So how should we factor these? What approach? The diamond. All right, we just talked about it. And I can do this for both the numerator and the denominator. So the AC diamond, all right, for the numerator, what are the factors? What multiplies to 3 and sums to 4? 3 and 1. For the bottom, what multiplies to 1 and sums to 2? 1 and 1. Okay, so for the numerator, I have 3x squared plus 3x plus 1x plus 1. Okay, so I'm just going to split this up temporarily. So I'm just expanding the middle term. And then once again, factor by grouping. What comes out of the first two terms?
3x.
What comes out of the second two terms?
1.
Excellent. Also notice that every time I always write this +1. Don't get lazy with your notation. I see it common that people drop that and then all of a sudden they have 3x times x plus 1 and it's just a mess. All right. And remember, at this stage, what can I do to make sure I did this correctly?
Times it out.
Foil, all right, or box, right? Foil or box, which is also part of the polynomial dance. All right, foil or box this back together, okay? Because again, they're just binomials. The whole point of factoring is factoring is the opposite of multiplying, okay? It's just cleaner than dividing. Okay, and then actually as a note, if the x squared term has a coefficient of 1. So when I did the AC diamond on this one, right, this was already 1. This case, I can actually jump straight to the factors. So this is just the C diamond. So I can actually jump straight to, that becomes x plus 1 times x plus 1. All right, so that's the quick diamond. And those are the ones where a lot of people even skip the diamond on those, and those you can go just to the binomial terms, which is absolutely fine. Because those ones I can see, we can all see. I was like, oh, x times x makes x squared, 1 times 1 makes 1, and then I could like foil that out quickly in my head. Oh, 1x plus 1x, oh, makes 2x. All right, so I was like, this case is not the case that really the diamond like thrives at, where it really shows how good it is. Okay, so all this comes back to three x plus 1 over x plus 1 divided by x plus 1 times x plus 1. And what do we see here? Let's plug that back in. Put our trigonometric equation back together. And is that what we were looking for? So again, we see these little techniques, converting it to another variable, All right, whatever is most helpful to you. If you can factor it all, leaving it as trigonometric functions, all right? But I mean, I see it all the time. Someone looks at it and goes, oh, I can't factor that. Hold on, take a pause. Now, is it possible that factoring might not have helped? Sure, okay? Those techniques are just the order in which you should approach things. But sometimes, oh, I did factoring, maybe factoring didn't help. So then I go to the next technique. Back up to all the way to the beginning and go to the next one, all right? But it's just practice, practice, practice. All right. The other big formula here, the sum difference formulas. These are actually very, very useful formulas. These are how the sum to product and product to sum formulas are created. All right. This actually, are we finally? Nope. Okay. We're finally at the bottom of the left side of that trig page. Okay. So we finally got through half of that trig cheat sheet. The point of these, all right, is that by identifying if an angle is a some combination, all right, sums or differences of common angles we know, we can identify more than our three common angles. What are our three crazy common angles? Almost 30, 60,
45.
45. All right. Pi over 3, pi over 6, pi over 4. Okay. Those three, all right, are our most common angles. I mean, minus 0, pi over 2 pi, you know, like minus the really, 90, 180, 270, 360, etc. All right. So basically, I want to find the exact value, right? Everything we do is exact value. So basically, I want to ask, can I rewrite pi over 12 as some combination of other numbers, and hopefully something to do with pi over 3, pi over 6, and pi over 4. So pi over 12 is 1/12. I know that that is smaller than all three of those, so I think it's going to have to be a subtraction. And then in order to get 1/12, what two numbers could be subtracted? Just in general, what fraction minus what fraction makes 1/12? How about 7/12 minus 6/12, right? Okay, 7/12 doesn't reduce, 6/12 reduces to 1/2. Okay, so that one is pi over 2. Okay, that didn't help, but that's close. That's what I'm trying to do. All right, so let me think what gets closer. How about 1/3 and 1/4? What does that become? So that becomes 4/12 minus 3/12. Does that make 1/12? Yeah. And oh, look at that. 1/3 minus 1/4. What angles are those?
Pi over 3 and
Pi over 3, pi over 4, right? I'm just dropping the pies, right? So I have pi over 3 minus pi over 4. So I was able to do this, right? Just by thinking, I need to create 1/12. And I was just gonna, if that didn't work, I was gonna test 1/6 and 1/4. And I was just gonna go through my three angles that I know the best, right? All right, so the point of that is, okay, so that's equivalent to that. Now if I use, right, the sum difference formulas, I can break up, right, subtraction or addition of two angles using this equation. So the cosine equation is the same thing, but opposite sign. And basically you have to identify which is alpha and which is beta. So I'm gonna call that first one alpha and that second one beta, and then I'm just gonna sub it into the equation. So cosine alpha, cosine beta. It's opposite sign, so since I had a negative there, all right, and that's what the formula says. The positive goes with the negative goes with the positive. Since I had a negative, all right, in here, that means, what is it out here? Positive. Okay, good. Just want to make sure that we see how the equation is written, because technically this is 4 equations combined into 2 equations, right? Because the sign is the only thing that changes. Sine alpha, sine beta. And why this is fantastic is because I know what all these angles are. Right? I know what the trigonometric function of all those angles are. Cosine pi over 3 is 1/2. Cosine pi over 4, root 2 over 2. Sine of pi over 3, root 3 over 2. Sine of pi over 4, root 2 over 2. Then all I have to do is simplify this down. Okay, so this becomes root 2. It's all going to be over 4 plus root 6 over 4. Right, we know when we have radicals, you multiply the insides, right? So everyone ideally should be able to get to here from here. But that's the point. I can now find more angles, more exact angles than just our 3 angles. And that's really the whole point, is we just keep expanding how many more angles can I identify? What did that say? Sine. Doing this in reverse. Okay, now here's the big thing, right? Ideally, we know this now. What's that? When you have different angles, what's that theorem that we love? Has to do with household pets. Cat, all right? Complementary angle theorem. What is important about using cat? The angles have to sum to 90. What are our angles sum here? 100, which means can we use cat? No, all right? And that's the big thing. You should always think cat first, and then look at the equation and say, can I use cat? No, which means I need to use something else. In this case, well, the something else, how about the sum to difference? Now notice how this one is written. Sine 80 cosine minus cosine 80 sine, right? So we only have 2. Which one is this one? Does this one become cosine with alpha beta or sine alpha beta?
Sine alpha beta.
It's sine alpha beta, because sine alpha beta has sines and cosines separated by the addition, right? With cosine, it's cosine, cosine, sine, sine. All right, so just being able to know that. Okay, so I know it's sine alpha beta. Sine of something, something. All right, then basically we need to pick which one is alpha and which one is beta and identify the sign. So which one's alpha, which one's beta? All right, match it up to the formula. Which one's alpha, which one's beta?
80 degrees is alpha.
Say again?
80 degrees is alpha.
80 degrees is alpha, right? That corresponds. Now, the truth is does it matter? No, because they're basically the same thing, all right? It's going to be better to pick the bigger value, and just for consistency, line it up with the formula. It actually just works out 80 alpha, 20 beta. All right? This is a subtraction of the 2. That corresponds to a subtraction or addition. Had a 50-50 shot. Subtraction here corresponds to subtraction here. Notice cosine was the opposite sign, right? That's what we identified. Plus becomes minus, minus becomes plus. All right? But for the sine sum difference formula, it's same sign. All right, so alpha equals 80 degrees, Theta equals 20 degrees, and it's the subtraction of the two. So this becomes sine of 60 degrees. And do we know what sine of 60 degrees is?
√3/2.
Yes. And so look at that, something that looks very, very complicated. All right, with the sum difference equation, also something that did not make 90, which is kind of our special number, okay? Using these sum difference equations, I was able to find what this was. And that's the whole concept of how we use formulas, all right? They simplify our lives, all right? Nothing we do is supposed to be complicated, right? Remember KISS. It's all supposed to be easy. Along those lines, speaking of cat, the definition of cat says, all right, this. We can actually prove this with the sum difference equations. Actually, all cat is a specific case of the sum difference formulas. So it doesn't really matter which one we do. Let's just do cosine. Using these sum diff formulas, this becomes cosine of my first angle, cosine of my second angle, opposite sign because the cosine one. If it's a negative inside, it becomes a positive outside, so opposite sign. Sine of an angle, sine of the other angle. And then we can simplify this down. Cosine of pi over 2, right? Do you remember how we do this? The other quick way to identify pi over 2, pi, 0, right? On the unit circle, trace it out. Cosine is x or y? X. Cosine is x. At pi over 2, that's up here. What's the x value all the way up here? 0. All right, what's the y value all the way up here? 1. Right, so they're always pi over 0, sine of angle 0, pi over 2, pi, 3 pi over 2, 2 pi, etc. It's always 0, 1, -1. That's it. There's only those options for angles on the axes. Okay, so pi over 2 is 0 times cosine plus sine of pi over 2 is 1. 0 times cosine goes away, which equals 1 times sine, which equals sine. And oh, look, we just basically proved cat. 90 degrees off, all right, of a co-function results in the other co-function. And basically, again, that's the whole concept. That's what cat is. The sum difference formulas, cat's just easier to remember because 90 is a really, really common angle, right? Pi over 2 happens all the time. The sum difference equations are much more generalized. They could do more, all right, but they're not nearly as common. That's why even on your trig cheat sheets, it's separated, right? It says co-function identities, then it says sum difference identities, because these cat co-function identities is super, super common. The sum difference proves it's the same thing. It's a generalized form. All right. So let's establish the identity. Cosine alpha minus beta all over sine alpha sine beta equals cotangent alpha cotangent beta plus 1. So as always, we want to grab the more complicated side. Which side is more complicated? Left. The left. It's actually kind of close here, right? But usually a division means more complicated, so I would grab the left. So convert to sines, cosines, common denominator, factor. I don't think I can do any of those here. What's the next one?
Identities.
Identities slash
Definitions.
definitions. All right. Do you see a definition in here? There's no identity here. This is more of a definition, but we can kind of use those synonymously. What definition did we just talk about? Yeah. More general. The sum difference. This is the definition of sum difference. Cosine alpha minus beta. Expand that out. The definition of the sum difference. And then actually, given that we're just looking for cotangent, something over 1, I was like, we're basically there. Just to further emphasize this, I'm going to break this up into multiple denominators. Multiple fractions, not multiple denominators. So this is common denominator in reverse, right? And we did that because sine alpha over sine alpha times sine beta over sine beta, what does that become?
1 times 1.
1 times 1. Oh, that second piece is super nice. What is cosine alpha over sine alpha? Cotangent of, now it starts to matter, alpha, right? So we gotta be careful when we have multiple angles. We gotta make sure that we're writing the angle as well and keeping that consistent. Because cosine alpha over sine of beta, that is nothing. Okay, if the angles don't match, that doesn't help us at all. Cosine alpha over sine beta, that's it. I can't do anything with that. But cosine alpha over sine alpha, that is cotan of alpha. Right? Cosine beta over sine beta, what is that? Cotangent beta. And then we already established that's 1. And oh look, that's what we're going for. Now, as a note, it is possible probably I could have started on the right side and converted everything to sines and cosines and then done common denominator, and actually I might have ended up back this way too. So, like I said, this one, it's kind of simple enough where sometimes starting on the left, sometimes starting on the right would have been about equivalent. All right, tangent sum difference formula, which is, okay, now we're literally at the bottom of the page. This one, not nearly as helpful. And mostly, I say this like, if we have the occasional angle that we're plugging in, all right? But converting tangent things to tangent things, it's not nearly as helpful because usually with tangent, what do we do with it? Turn it into sines and cosines. It's way more helpful. In a similar fashion, okay, so I have kind of a variation on cat here. Pi over tangent of pi over 2 plus theta equals negative cotangent. So that's almost cat, just a slight variation. But the whole point is that this is just not as useful. Because I don't think even turning this into that formula is going to help me. What I want to do is what we normally do, which is I have tangent. I want to turn that into sine over cosine. then I can use those individual sum difference formulas. Okay, so writing out my equations, all right, writing out my sum difference equations fully. Then what should we do? No one knows. Pi over 2. What is pi over 2? 90 degrees. It is a specific angle. Do I know trigonometric functions of a specific angle? Yes, especially pi over 2. Again, that is a big one. What is sine of pi over 2? 1. What is cosine of pi over 2? 0. And as soon as I know something is 0, does that mean a bunch is going to go away? Yeah. So when you have a specific angle, I know on some of these, right, all we have is alphas and betas. Alphas, betas, thetas, gammas, right, deltas, epsilons, all we have are Greek letters. Pi is, yes, technically a Greek letter, but pi represents a number, all right, aka specific angles, all right, when talking in trig, which means we need to actually plug it in. Always turn it into a number whenever you can. So sine of pi over 2, that's 1 times cosine theta plus sine theta times cosine pi over 2, 0. Cosine pi over 2, 0 times cosine theta minus sine pi over 2 is 1 times sine theta. Bunch of ones and zeros, so all I'm left with here is cosine theta divided by negative sine theta. Cosine over sine is
Cotangent.
cotangent. And oh look, that's what we were looking for. All right. Really, really good stuff. Inverses. When we have inverses, all right, we've talked about this a few times now, so hopefully it's starting to click. When we have inverses, what's the best thing to do?
Isolate the inside.
I can't isolate the inside. I was like, I think I know what you mean, but when you say isolate, that usually means like isolate the square root. All right. It's not quite isolate, but what if it was just sine inverse, or actually not that one, sine inverse of cosine inverse of v? What were we doing before?
We've let theta equal over.
All right. Well, when now you have 2 of them, we just let each one of the inverses be an angle. And that's basically the whole concept. Let theta equal sine inverse of u, and let gamma equal cosine inverse of V. So we have to convert the entire piece. So what this part becomes, this becomes sine of theta plus gamma. And what are we going to do with this theta equals sine inverse u and gamma equals cosine inverse v? Trig's all about what shape? Triangles. We're going to make the triangles on those individually. So I can go and I can make the triangles on these. But before I do that, so I'm going to be able to find exactly what I'm looking for here. This here is sine of theta plus gamma. What is this? How do I deal with this thing? What have we been talking about all class? Sum difference. That's a sum difference equation. All right? Sine of theta plus gamma, I have no idea what theta plus gamma is. But if I use the sum difference formula, the sum difference equation says, all right, that sine is sine alpha, right? Alpha beta, all right? This then turns into sine of theta, cosine gamma, sine gamma, cosine theta. That, if I just have a trigonometric function of a single angle, I can find that. All right, in order to do that, so let's go back to our triangles. So we have theta equals sine inverse of u. Right? Take the sine of both sides. That means sine theta equals u. And SOHCAHTOA, right? Remember, all trigonometric functions are something over something. That means this is u over 1. From that, I should be able to make a triangle. And so here's my triangle. There's my angle theta. Sine is what over what? Which one over which one? Which side over side?
Just over the hypotenuse.
Opposite over the hypotenuse. And once again, how do I find the missing side?
Pythagorean theorem.
Pythagorean theorem. So that's the adjacent. A squared plus u squared equals 1 squared. Solve that down. A equals square root 1 minus u squared. What's my one? Gamma equals cosine inverse v. So similarly, we said let gamma, and again, I'm just picking an angle. If you, and I'm picking all the Greek letters, but if you want to just use A, B, X, Y, right? It's absolutely the same. And now I can make my other triangle. And cosine is which one over which one? Adjacent over hypotenuse. And similarly, that means this side is 1 minus v squared. So I've created my triangle for the angle gamma. I created my triangle for the angle theta. And so now back to what we were looking for. Okay, sine of theta. Oh, actually, I already know. What's sine of theta? And now I can just plug these in a piece at a time. So that one's u over 1. What was cosine of gamma?
D over 1.
What is sine of gamma?
Square root 1 minus v squared over v over 1 over 1.
Over 1. Right? Opposite hypotenuse. And lastly, what is cosine of theta?
Square root 1 minus u squared over 1.
Again, I'm just doing SOHCAHTOA. Creating the triangle, that's the quote trick, but it's literally this simple. And I see people just struggle over it all the time. Inverses is something I don't know, but sine of an angle is something I do know because I can always create the triangle. Square root of minus u squared. And then I can simplify this down, and this actually simplifies pretty nicely. uv plus square root 1 minus v squared times 1 minus u squared. And be aware, right? Square root of 1 minus u squared does not become 1 minus u, right? That doesn't work. Square roots do not distribute across addition, right? They do distribute across multiplication. You have 2 square roots being, you can multiply the underneath, okay? But you can't, I can't take it into each individual piece. Again, that's an algebra thing. And that gives us what we were actually trying to find. Are we okay? That's just a complicated version of basically everything we did in the first section of this chapter. All right, and let's establish one more identity. Okay, so left side, right side. Left side. I was like, now be aware, on the right side, that's cotangent alpha minus beta, which means what should jump to your mind?
Some difference.
Some difference, okay? So this is probably another one where I could start on either side. I'm going to start on the left side, all right, because it does look, I already feel like I can do more. But I mean, if I started on the right side, I could turn that into cosine over sine and then expand out to some difference. And I see a lot going on there already. So actually that right side, I want to point out, don't be like lost of that side is bigger than this side. This side is actually pretty complicated. And our goal is to start on the more complicated side. But it's really whichever side you feel like you can do the most on. So I'm going to start on this side because I already see a bunch we can do here. But I bet I could get just as far on the other side. All right, so we're on the left side. We're going to start here. What do we think we should do? Jada?
Change to sines and cosines?
Absolutely, right? I have cotangents all over the place, which means I know that that's sine over cosine or cosine over sine stuff. All right, that's converting to sines and cosines. All right, what else do we see? What do we see we should do next, maybe? equals out.
Common denominator?
Common denominator, absolutely. Specifically, common denominator among the numerator, common denominator among the denominator, because what am I going to want to do? Next. We do common denominator among complex fractions in order to what?
Rid of the fraction.
Well, we can't get rid of fractions when, if we're not solving. Oh, that factor.
Leave it
Leave it, change it, flip it, right? That's why we make the common denominator, because this is a fraction. These are fractions within a bigger fraction. So leave it, change it, flip it is basically where I'm going to be going. But absolutely, let's do common denominator. All right, so this guy becomes cosine beta. Okay, so common denominator. Then, all right, I'm going to put it all together as one big fraction. And actually, we can leave it, change it, flip it all in one step too, just because it's a lot to write. So putting it under one denominator and then leave change, flip. And it kind of, again, did that in one step. If you need to go slower, you can definitely go slower there. But that just happens to be something where we can see what's happening, right? And then what do we see here? Yeah. And then cosine alpha, cosine beta plus sine alpha, sine beta. All right, sine alpha, cosine beta minus cosine alpha, sine beta. What are both of those?
Just go back up quickly, please.
The sum and difference identity.
These are both definitions of sum difference. All right, so the only thing is identifying which is which. All right, which one's the numerator? Cosine, cosine, sine, sine. That one's cosine. All right, something about alpha and beta. All right, is it subtraction or is it addition? It has a plus there, which means it's the opposite sign. All right, cosine is the flipped one. Okay, sine, cosine, cosine, sine, or sine, cosine, however you want to say it. All right, so the denominator one, which one is that one? That one's the sine. And if I have a negative there, that means what is it? It's also, that one's the same sign. Which cosine over sine? Which gives us cotangent of alpha minus beta. And is that what we wanted? Yes, it is. This is another part right here, though. Cosine of alpha minus beta, sine of alpha minus beta. Cosine of alpha minus beta divided by sine of alpha plus beta is nothing. Again, when we start changing the angles, it's important to know that all those reciprocal identities and quotient identities, it has to be the same angle inside. Way too often I see people, oh, it's cosine alpha over sine beta, and then they just turn it into cotangent. All right? It has to be the same angle for those identities to work. All right. Just all kinds of good stuff, right? Are we getting better? How are we doing with establishing identities? Good stuff? Practice, practice, practice. Just grind those through.